All right, guys, let's get started. Why is this not working? All right, there we go. So today we will share this one. Currently recording. All right, so let's begin. So let's take a look at the calendar. I've updated the calendar now. We're pretty much at the end of the semester. If you haven't noticed, we're literally here, right? April 4th. So we've got 4 weeks, exactly 4 weeks until finals. Okay. So today is April 4th. We've covered in the last 2 weeks, neural networks and the intuition, a bit of history, the perceptron fit function with NumPy, and then linear regression last week. Today, we are going to look at logistic regression, which is an extension of linear regression, and also the multi-layer perceptron. Okay, so if you remember, you've already looked at the multi-layer perceptron when you did your WECA assignments, right? So this time we're just looking at the algorithm. You already know how to use the tool for this. And so this is kind of the week where we kind of jump into neural networks themselves with the multi-layer perceptron. You notice on April 13th, the last, this day and then this week, we will jump into deep learning and Keras. And what's interesting about this is that really there isn't that much anymore, right, to add. So it'll be very straightforward. You'll know pretty much all the theory even before you get to deep learning. Okay, so you should understand how the algorithm works by then. But I will introduce a couple of new tools, or one new tool, TensorFlow library, and then Keras, the Keras also module in TensorFlow, which is now part of TensorFlow, which will allow you to just more easily create deep neural networks. And then remember, you have a term project. So hopefully, I know some of you have picked a topic. If you haven't done so already, it's very important that you pick a topic. Since we're a small class, we're just going to do this individually as we've done before. And it's basically a supervised learning problem, right? So in line with what we've done before, just make sure you will have to apply pretty much all the algorithms for supervised learning, including deep learning. And that's the reason why on April 20th, I'm kind of leaving that day as a work on project day. I'll help you out, if there's any tweaking that needs to be done before your presentations on the Monday, April 25th. Does that make sense? So April 25th, we'll just do presentations of your projects. I'll do a course summary and wrap up on the 27th, but basically that's it. So if you think about it, deep learning is not really that complex. It's more about learning the code. So really, this is the last lecture today that is like in theory, like heavy on theory, right? But it wraps up everything for it. Okay. So all right, so that's the idea. Also, I remind you that April 11th, which is next Monday, I will be out of town. So no meeting here or Zoom, right? Instead, it'll be exam 2. Okay, so that basically means that at this hour, at 12, the exam will open on Brightspace, and then you guys can complete it by 2. I'll be checking my email, but I'll be at a place, so like a conference type of thing. So You know, I'll be monitoring, but just via email if you have any questions. But otherwise, you know, it should be pretty straightforward, like the first exam. Are there any questions about that? Very similar format to exam 1. It's comprehensive, right? And you know, I'll give you some problems, and then I'll just ask you to solve them. Pseudocode, Pythonish. It's fine. Okay. All right. Anything else? Nope. All right. Great. So that's the calendar. I always like to, you know, I like to know very clearly what's going on. So then, as I said, this week, logistic regression and multi-layer perceptron, we're making that jump into these two. And then you'll see the algorithm is actually just a little extension of the perceptron. And then linear regression was an or actually, I should say logistic regression is an extension of linear regression. Linear regression was an extension of perceptron. So it's almost like very incremental to the point where it just, you'll be like, okay, that's it. But that's it. You know, I can't really stress. So today we're making the jump from linear regression to logistic regression. That's the only thing. So we'll talk a little bit about that. And I'll jump all the way to the multi-layer perceptron, basically. Start here. All right, so we're going to switch over then to the whiteboard. I'm not hearing any questions. Just to remind you, please start thinking about the project. And then you have one homework assignment, I think, right? Just that one. So you got just those 2 things. I'm not going to assign anything else as far as homeworks. I mean, we're kind of at the end, but work on the project. Do a good job on the term project. All right, so let's go ahead. So as you can see, the sequence has been, you know, we started with the perceptron, and you've seen how that algorithm works, basically. And then then we jumped into linear regression. Right, and you saw how that works. And now I've said we're moving into logistic regression. Right, and then there's that. And then multi-layer perceptron. Multi-layer perceptron. And notice they both have, you know, it's the same name, right? Perceptron. This is just a multi-layer perceptron. And then finally, deep learning. So if you notice, this is the best sequence that we can look at. In the perceptron, we kind of just had this idea, right? You know, something like that. That started to become formulated where we had a threshold, basically. You know, if greater than 0, then 1, else 0, right? And so we did that in the first example. In linear regression, basically we are doing WX plus B, right? And we are predicting values that go from -infinity to infinity. So any real valued number, okay? That's it. And then we've got, in logistic regression, we've got something similar. But now, the Y we're going to rename Z, and that's only because we want to run Z through a function, and then that becomes Y. Do you see that? That's the only thing. And the mapping here happens so that the values go from 0 to 1 instead of from -infinity to infinity. So it's been narrowed down. And this really becomes like this idea of a probability. How likely is it to be this thing versus that thing? Well, if it's 0, then it's low probability. If it's 1, it's high probability. That's kind of what we're going to try to teach our machine here. And then the multi-layer perceptron, then basically this assumption, but just elaborated a little bit more. Okay, because we look at things from different points of view. So in the multi-layer perceptron, it becomes something like this. So if you look, we're going to say Wx plus B, but now it's going to be Z, and then this Z becomes FC, but it's no longer just Y. Notice here the difference, it is going to be H1. Do you see that? And then instead of X now, another set of weights times H1 plus B equals, so this is now Z1, this is C2. Does this make sense, guys? And then we just run. So this now is C1, and then this C2, F, and now it becomes Y. You guys understand? That's all, that's it. As far as architecture, right? So as far as architecture, we started here with linear regression, right? And even this one is like this, but we just have like a little trick, right? So Y equal Wx plus B. So this was, if we look at the perceptron algorithm, the function, so if I look at the perceptron, or actually, where am I doing this one? So if we go to the GitHub, right? Oh, I need to share. Here. Okay, so everyone should be seeing GitHub. Here, look at the perceptron code. It's the same function, right? You know, this one, there's an activation function associated with it, right? We have the update rule, etc. And this is just a perceptron. So it's very, you know, very basic. But what makes it different, really, the perceptron and logistic regression, the equations are not different. What's different is the update rule. The update rule, as I'll see, there's another component to this, and I'll try to mention that in that same graph. If I have room, that's going to be different. But if you look, this equation np dot x times weights plus bias, and there's even an activation function here in the perceptron. So if we go back to our whiteboard, this one, so actually, let me be consistent here. I'll keep that. And then this one is actually pretty consistent with right, and even has, so it's even a Z. Run through a function, and then that gives you Y. But here, this is different, right? In logistic regression, we kind of have the same thing, and these also go from 0 to 1. But the optimization, let's say, the way that we find, the way that we do the updates, right, it's going to be different. So let's just say here, I'll use a different color, simpler update, or optimization. Whereas in logistic regression, we're going to have more advanced, if you will, optimization. So let me actually, here I'll say they're both very similar, perceptron and logistic regression. Well, I mean, they should be, right? So they're just an escalation, but from here on, better, let's say better update, the update rule, which basically means optimization. It's the way that we do the update, right? It's the way that the update is supposed to happen, which basically means it's supposed to be, because there's the prediction of things, but then there's this, right? The calculation of the loss function, really this little thing where we take the difference of something and the other thing. So that's really what makes it a little bit different. All right. So the better update, and actually this one is called cross-entropy. So it actually comes with a name. Okay, that's going to be the optimization. So we're going to take a look at that one. And going forward, they all use the same. So this is actually this one. So this one is going to be, again, better update. At the end of the day, a lot of these algorithms over time just try to improve on this, right? So they try to improve on the little parameters, but they all use going forward pretty much cross-entropy, especially for supervised learning, right? So when you're doing that type of classification, you're going to use cross-entropy. What is classification? I mean, when we're trying to classify between classes, like in iris data is setosa, virginica, versicolor. Right, so this is supervised. Oops. This is supervised learning. So that's supervised learning. And that's what cross-entropy is for, okay? So supervised learning. So supervised. Now you can do other things with neural nets, but that's a much more advanced topic, so we're not going to worry about that, but just keep that in mind, okay? Now, linear regression, if you notice, I left this one kind of different here. Usually the optimization for this, which are referred to, the terminology is the loss function. So optimization. And they're referred to as the loss function. Here we use least squares error. So LSE. Sometimes mean squared errors, but least squares. And that was the other one that, where we had the other intuition. So this is called least squares, or MSE, sometimes mean squared error. So it's a different function because we're trying to do a different objective. Do you guys understand? So you usually have, and then deep learning. Let me just finish here with deep learning, and then we'll recap. But this turned out to be a nice slide, actually, of the differences between all of these and how they build on top. And there's basically like two things going on, okay? The red and the blue. And then there's a whole bunch of other things as well. So look at this sequence, right? What do you think? How would deep learning, let's say this was an exam type question, right? And I ask you guys, so how would deep learning be different? What would you guys say? So if we go back to the slides, how would deep learning be unique or different? What do you guys think?
How would deep learning work? Deep learning would just be multiple different input layers of a neural network, more than 3 layers.
So in this, what I have there, infer. Elaborate.
Oh,
It's right there. Several Z's, right? Exactly. Several C's. Very good answers. Good answer. That's it. So you know multi-layer. You sense the point that you understand logistic regression, which has a lot of similarity to linear regression. You already understand deep learning. Deep learning is no mystery, right? It's the same stuff as before, just these additional Z's. Exactly. So now if you look, I'll start over here. And just remember, all of these W's are different. Okay, even though I'm not doing, I should have done 1 and 2, but sometimes I'm bad at like putting in the subscripts, but they're all different parameters. Yeah, they all need to be updated. And that's why you need to backprop, right? So remember, let's look at the multi-layer. You start here, you end up at Y. This Y gets compared to the labels. And then once you know the difference, you work your way back to the beginning. And so W2 and B2 updates first. And then with that, you update W1 and B1. You guys see that? So for instance, here, see if I can generalize this one. It would be W1, the original X. So the original X goes here, right? The first input, the image of a cat or whatever it is. And this predicts C1. And then notice I'm just using a generic function, but I've already introduced one function last week, the step function. Do you guys remember that one? The step function, which was who did we say used the step function? I have it here actually. I drew it. There it is. Right. So that's the step function. I think I did this in class too, right? The stepper function. So it gives you a 0 or a 1. All right, so that's this, right? So technically, this F here is just a step function. You see that? But I don't want to get into that because it's not so important. So, or it is important, but it's not complicated. That's what I'm trying to say. So just keep in mind there's an F, right? That the Z value goes through the F function to be modified to, instead of, if you just do it like this in linear regression, there's no function, notice. So it's just any number, whatever, whatever your data is, it'll learn that, right? It'll learn to predict the mass of black holes, which could be really large, or the mass of particles, which could be very small, I assume, right? Something. Or it could be the housing prices or your favorite, hat or something like that, okay? So, but anyway, the function just does that. So they all have functions basically, except linear regression has no function. So that means that you're really, for all of them, you're trying to do this, 0 to 1. Now, it doesn't have to be 0 to 1. It could be, for instance, -1 to +1. That's the tangent, I believe. Sigmoid is 0 to 1. Stepper function is also 0 to 1, but a hard 0 to 1. You see that? So this one is just 0 to 1. Logistic regression is 0 to 1, not 0 or 1, because it tries to be a type of a probability. Right? It tries to be a probability. Okay? And then this one is just any number. But you have the optimization here. So there's always 2 elements, the red and the blue. And then here we run the Z1 through the function, and that gives us H1. But then now W2 H1 plus B2 gives you C2, as you said, right? So C2, and then C2 goes through the function, and that gives you H2. That gives you H2. And literally, when we start to implement these, especially in TensorFlow, TensorFlow is meant to look like that. So you'll see how we're actually going to do, you know, all the TensorFlow, PyTorch, all the libraries try to do this. They express neural networks as these functions. I'm just going to generalize here, dot, 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 because a deep neural net could have many layers. I think the famous ResNet convolutional neural network that everybody uses for image processing, it was trained on 1.3 million images of something called ImageNet, I think. It's probably bigger now. And everybody just uses that whenever they want to classify images. They use that pre-trained model and then just fine tune it with their own data later. That I don't know how many layers it has, but I think it has, some versions have 32 layers or more, right? And those are like blocks, actually. There's more layers in each block. So it's like you have to treat it as not 32 layers themselves, but blocks made up of layers. So it's easier to interpret. And then this one would go all the way to, let's say, so if I generalize, this is Y, this would be F ZN, which means CN, yeah, would be WN H N minus 1, right? Plus BN. Do you see that? That's the generalization of a deep neural network. And in between, you can have as many layers as you want. Now, should you have a million layers? Probably not, right? Because first of all, your computing power, there's limits, right? That's why we need GPUs. That's why we need, I'm currently using a GPU box that has 128 RAM, and it has one NVIDIA RTX 2080, I think. It's good. I mean, it's a powerful computer. I'm sure for those of you that are gamers, you probably have the same thing. It's a standard gamer computer type, but that's a good, good amount of memory, and there's limits to what it can do, right? It's like it still takes me a day or two to process something really large, like 2 million records. A lot of records. It's how it is now. I think I mentioned this. There's a deep neural network that was trained on 2.5 terabytes of data. Question. I think Google did the original BERT system, and then this is a Roberta system. I believe whenever it's Roberta, that's a Facebook. But, they have a rivalry, so they kind of, I think it was Facebook that did this, yes. 2.5 terabytes. And that was some time ago. And I think I was pretty surprised at how many, I don't even know. Because I read the specs, but sometimes I think it can't be that they use so many processors, because they have a tendency to want results fast. So they don't want to take 36 days so they just and they have, I think nowadays, I think it's realistic, but maybe we're up to 1,000 GPUs processing something. It's possible. Don't quote me on that, but that's where I feel things are. And there's TPUs. I don't know if you've heard of those. A TPU is a tensor processing unit, whereas a GPU is a graphics processing unit, right? TPU is Google's version of a specialized GPU. So they created their own architecture based on GPUs, but they call it TPU. Apparently, it's even more optimized for machine learning, whereas GPUs are also for graphics, right? Computer games. It's not sold to the public, but you can use it in the cloud. So it's a cloud service that they're trying to market as with everything Google. They're trying to sell you something, huh? Yeah. You can use their cloud TPU for sure. They had no, it's free for the beginning. They kind of want to hook you in. They have a thing called Colab. I don't know if you guys have heard of it. So Colab is a thing they have, And you can download it. And it's like Jupyter notebooks, like the ones we have used in the class, but their own also, colon. But you sign in, you see, and then now they own you. So that's why I'm always a little bit reluctant with them. When they make things too easy like that, then you don't learn the stuff that you should be learning, right? And eventually you just rely too much on them. So that's why, but it's good. I mean, it's certainly, as in data science, you should definitely know it. I mean, you have to. It's like that. You gotta know everything, and by the time you master it, it's obsolete, and then learn the. Anyway, but yeah. So hopefully this makes sense. I like this slide actually, how it turned out. Then we're gonna look at the diagrams themselves, but you can see here this is deep learning, and then this is a multi-layer, and then so multi-layer simply means that it has one hidden layer, the H1, whereas this one can have from H1 to basically Hn minus 1, right? So whatever that number is, and it can be pretty large. And hopefully this explains why you have so many parameters, right? Now remember that you have here an X, but X could be the 4 features of Iris, or it could be the 784 features of MNIST, every image, or even larger. I think currently deep learning supports images of 300 by 300. So believe it or not, if you gave it a high definition image, you might think, oh yeah, I'm sure it won't be able to process. Impossible. Deep learning has current limits. So if you have a high definition, if you have high definition images, you gotta, yes, make them smaller, downsample them to about 300 by 300. I believe that's where it is right now. You mean send them back? Well, just to teach the. Well, no, actually, so what it means is that every image that goes into the model needs to be downsampled to 300 by 300 because it was trained on images that are 300 by 300. Do you know what I mean? So it's anything bigger than that, it'll just like run out of memory. The operations will not be able to. And so usually with the algorithm that you should be using, which is CNNs for image processing, that's kind of like the state of the art. And but yeah, you have to, let's say you have images and they're all high def, and you got to downsample them to 300 by 300. Train the model with those, and then whenever you get a new one, like a test case, that also needs to be to 300 by 300. Those are just the limits. You can't do anything about that right now with current technology. Even with the TPUs of Google, I think. Because I don't think it's much more, it's like a little bit more efficient. You know what I mean? But it's not like many times. Yeah. Huh? Exactly. All right. So this is where we are. And then of course, after this, there's a generic set of deep learning algorithms. And then there's the advanced or specialized set of deep learning algorithms. We are not, of course, going to get into those. Some of those can be very difficult to understand. We have a grad level course, ITS 530 and 520, where we cover a little bit more of the algorithms themselves, but they're like grad level classes or senior standing. But we will go as far as this, right? So in this class, but you will use TensorFlow and Keras next week. And as you will see, it'll be pretty straightforward. The code is already on GitHub. You can take a look at it if you like. But anyway, these are the differences. So if you look, the functions are here, and you can see how they just become a little bit, more. And then of course, there's the optimization. And what do I mean by the optimization? The update rule. How do we update the weights, right? That has been the theme that we've been discussing all, in the last couple of weeks, right? Doing that update, and we've done it manually with the perceptron. It was really easy to do, and then we did it also with linear regression. And so now we're just going to look at it from the point of view of logistic regression. But before I talk about optimizations here, and also I want to say here, This is 0 to 1. 0, remember, these are 0 to 1, not 0 or 1, as in the perceptron. So the next thing we need to think, well, we don't really need to talk about, I guess, the optimization for perceptron, but we do need to talk a little bit more about least squares, and in particular cross-entropy. So we have to develop an intuition for these, okay? Just remember that this was a simpler update, whereas these optimizations are better updates, okay? You know, they become more sophisticated. And this is where the algorithms come in that we had talked about, you know, feed forward algorithm, back propagation, and stochastic gradient descent, okay? And there's quite a bit that goes into this in the backgrounds, but that's why we have libraries like TensorFlow or PyTorch, which basically abstract a lot of the things going on in the background, so that we basically end up just defining the architecture and the optimization function, okay? So let's talk a little bit first, before we talk about optimization, let's talk about the things in red here. This is usually called the architecture, all right? So we're gonna talk about the architecture. We've seen it, how we would write it in a functional way, just by function calls. Now let's see it, how we would write it in a diagram, okay? So that, you know, I'm gonna do the exact same thing. So I have the perceptron. I have linear regression. And then I have logistic regression. And then I have, multi-layer perceptron. And then I have deep learning. All right, so let's change colors here. So now we're going to think about it from the point of view of the diagram. So it's called neural network. So everything is represented as a neuron or a link, right? Remember, the neurons can be quite a few things. They can be X's, they can be the Y's, right? We represent the weights as just links, right? But, you know, everything else as neurons. So here we have something like this. And remember, this has, whenever I draw something like this, it means there's some kind of a function. Now, we actually like to group things like this, and that just implies the layers, right? So this is the input layer for the perceptron, and this is the output layer, right? And these are the weights, basically the connections. And that's kind of what a perceptron looks like. Keep in mind, there is a function here, right? The what is called the activation function that it runs through. Linear regression, on the other hand, and remember, this can be however ... Linear regression, right, is also the inputs to an output, but there is no activation function. What that means is it's just basically like this, you know, whereas this produces 0 or 1, this will produce minus infinity to infinity, but it just looks like this in diagram form. So no function, okay? Logistic regression can have a couple of ways of being written. So I'm going to draw that, a couple of diagrams. Okay, so it could be the inputs. Okay. and like that, or it could be like that. So what that means is we can have either one neuron as an output, right? Or we could have multiple neurons as outputs. Usually though, we keep this small, okay? So we're not gonna keep this very big. You guys see that? So that's basically, and then this one also connected like that. Now, what this means is, for instance, in this case, this is a good representation of saying, is this true or false, right? So what is the probability that this is, you know, something like a binary type of a class, right? You know, cat, not cat. So what is the, you know, you give it a picture of a cat, what this will return is a value between 0 or 1, not, oh, sorry, 0 and 1 between. So what that means, if it could return 0.5, which means it's really uncertain, right? Or it could return 0.1, which means not a cat, closer to 0. Or it could return 0.9, which means, yes, I'm sure it's a cat. You guys see that? So that's an interpretation. Another interpretation of this is that, just draw that a little bit better. Another interpretation of this is actually cat or dog. You see that? So in this case, we have a two-class problem, and the neurons represent this. So for instance, here, you know, in its simplest form, the logistic regression algorithm would return what? A vector of 2. Do you see that? Whereas here, it only returns a vector of 1 value. Here, you give it the picture of a cat or a dog, logistic regression will return. And also, remember, there's a function involved here for both. So I'm just going to put in fx. Maybe, you know what I'm going to do? I'm going to do this. So whenever there's an activation function, I'm going to put another one in here. So this and that. Okay. But in this one here, it will return a vector of 2 values, one for cat, one for dog. This value should be what? If it's a picture of a cat, what do you think it could be? Well, if it's a picture of a cat, this would be probably 0.8, and then this one would be what? 0.2. Perfect. And that's you assuming that they add up to 1. So you use that assumption, which is a good one, but it requires a different activation function. So that actually is a good segue. So if this little green thing, right? If we're mapping to values from 0 to 1, then we use something called the sigmoid function, which is like the stepper function, right? It's got an S shape. But if we only use the sigmoid, actually, the values don't necessarily add up to 1. So what that means is that this could have been simply 0.4. If we look at those two values, they don't add up to 1, but we still, it still works. We just pick the highest value. Does that make sense? However, if you want the behavior that Jake said, then you use something called the softmax. And you'll see this a lot. The softmax function is actually the right function to use here, because the softmax not only produces values 0 to 1, but ensures that the values add up to 1. It makes it even better, right? It's a better precision. Usually if you're doing one algorithm with just sigmoid versus an algorithm with the softmax, the one with the softmax might perform better, even though the one with the sigmoid could be good enough for certain problems. Got it? Any questions about that? These are all activation functions. So maybe I should mention, it's a good time now since we've accumulated a good set of them. Activation functions, there are several of them. There's the step function. We saw that one, right? I've talked about sigmoid. There's the tangent, tan H. There is, there's the softmax. There's one called relu. There's one called gelu, and so on. Do you see that? And there's many. And what all of these do is they take an input from the linear and map it. So for instance, the stepper function is the one that I gave you guys that looks like a step. You see that? It gives values like that. The sigmoid function looks like that. It's kind of like a step function, but a little bit more curvy. So it's not a hard 0 or 1. It is, whereas this is 0 or 1, right? There's only that, right? So, you know, the values are always either 0 or sorry, -1. Let's say I should have shifted this up. So just shift it up. This one gives you, and also they're not shifted correctly. Both of them are not. So it should be like that, right? 0 or 1 on the y-axis given the x-axis. And the same goes for this one. Like that, where this is 1. 0. So they're like that. Tangent, if I remember correctly, just shifts down, I think. You'll have to look this one up, but I think this one is actually tangent. So it's the same S shape, but just shifted down to from -1 to 1. Do you guys understand? So this is crucial because now you get these different kinds of outputs. Do you see this? What would this one be? Exactly. And then softmax is the same thing as these from 0 to 1. So it's kind of like an S shape, but the values add up to 1. So let's just say like sigmoid, but values add up to 1, which is more intuitive, right? That was your intuition to go with that. And somebody said, yeah, that's what we're in. It sounds intuitive. So let's do that. Relu is interesting. And actually gelu, I just read about yesterday. So I have no idea. I haven't looked at the difference, but I found it interesting that they were recommending this one. I'm sure it's a variant of Relu, but I'll just say Relu is, Relu looks like a hockey stick. So let's go with red here. That's the idea with Relu. And so what that means is that it is like this and then like that. So how would you interpret that function? What does it give you on the output here? If this is y and this is x, to x, right? Whatever x is, because it gives you that same y. It's linear. So that's why it's just remember, it's a hockey stick. So it's a hockey stick. So it makes everything -0. And then after this, not anything. It will be whatever the input is. Whatever remember that in all of these, look, Lenny, here, see, in all of these, we plug in not x, but actually I wrote that incorrectly. It's z, right? The logit. So we plug in the z in all of these. Z, and then the values are mapped to these. So that's where those activation functions come in. ReLU, for whatever reason, experimentally, let's just say, has been found to be the best for deep learning, actually. So you'll see probably when we do deep learning next week, you'll see me use the ReLU activation function. Yes, it stands for rectified linear unit. So it's a linear unit because it's linear here. Oops, that's linear, right? That behavior. But it's rectified, which I assume the rectified part is this over here. I don't know. I just read about that one yesterday. I literally, like, I was surprised that I was reading about this deep learning algorithm called the transformer, and they said we don't use ReLU anymore. We use Jello. so here it is, PyTorch. It's called the Gaussian error linear units, which kind of makes sense because everything is all, you always want to normalize things, right? Gaussian comes from the normal distribution. You guys remember in the Bayesian algorithm, we looked at that function, the Gauss function. So that's what so I should have guessed that it was something like that. It's like a hockey stick, but actually, I keep doing it on my laptop. We share this screen. I think this is exactly what I was looking at. See, this is the Jello applies the Gaussian error linear units, takes in an input. And basically the shape seems to be almost like ReLU, but you can see it's a little bit curvy now instead of it being a. Huh?
Just a little bit.
Just a little bit, yeah.
Why does it go below 0?
I don't know. I just read about. Huh? If it's not, if it might be that it considers that this transition point might be important. Maybe. It wants to have, I mean, if you think about it, it wants to have a little bit negative at some point for whatever reason. That would, I mean, by looking at the graph, that would be my intuition. But as I said, these things, like I literally just read about this, so I don't know. I mean, when me reading something, I'm always like 2 years behind, so it's not necessarily new. I just read about it. Yeah, it's different. Yeah. Yeah, so I mean, here's, you can read about it. You can see Jello, the Gaussian error linear unit is an activation function. And it runs through the standard Gaussian cumulative distribution function. Yeah, so it's so you'd have to get into it, but you can see the intuition is to consider normal distributions in there. All right. So anyway, so we jumped to activation functions and we kind of discussed those. Now that you have an understanding of how these work, we can go back, right? Go back to what we were doing. And if you notice in the previous slide, we looked at it from the functional point of view. Now we're just looking at it from the architecture diagram form point of view. And then we'll come back, we'll wrap up today with the blue part here, the update, what you know as the update, right? But the update is based on, the optimize is really called the optimization, the loss function. There's always two main equations. There may be more, but there's always two main equations to all deep learning algorithms: the inference function and the loss function. What are those? This is the inference function. Why does it mean inference? Given some x, you predict some y. Do you see that? So given some x, you predict some y. 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 That's the inference function. It's gotta be there. And then there's the loss function, which is the other equation that tells you the behavior of how you learn, right? And we'll wrap up with that here, but let's just now go to this one over here, which is the diagram form. So let's continue with this analogy. So we were at logistic regression, and we said that we have some inputs. We can have an output, which is just one neuron. Usually when you have a binary problem, you can do this. Is it a cat or a dog? So what is the probability of it? Well, because we're running it through a sigmoid 0 to 1. If we're running this with two neurons like this, where we actually have two classes, and we want to say, is it a cat or a dog or more, right? Let's say, is it a cat, dog, or bird? All I have to do is add a third neuron here. You guys see that? That's it. And so now we can say this is cat and dog. When we do the training, we don't actually say, in this sample of a cat, it is 0.80 cat and 0.20 dog, right? That wouldn't make sense, right? Unless we had like a combined thing of how many cats, but that's not what we're doing. So we're giving it a picture of a cat, picture of a dog. So we don't say 0.8 cat, 0.2 dog or whatever. All you say is you're sure of what you're looking at, right? So what would be the intuition then? What would you say? Yes.
So let's say if it's 0.8, like a 0.8 is like 80% cat, so then it's going to be a 1 that's 80% sure it's cat. Let's say it's 0.1, it's like 10% sure it's cat. So it'll mark it as 0.
You have a picture of a cat. This is a cat. You know it's a cat. There's no doubt about it. It's a cat. But you know that the algorithm is expecting 2.
Yes.
So how would you encode this? If you know it's going to predict 0.8 and 0.4, and you just pick the highest one, but you don't have to say 0.8 and 0.4 because it's not 0.4 dog. It's what dog? 0. Good. So if it's 0 dog, then it is. Very good. Does that make sense? That's how you do it. So so when you train, you just say 1 0 or 0 1 or 0 1 0, depending on the class that it is. The algorithm will not be able to be that precise because but it will be as precise as this, which would be sigmoid, or even better, Softmax, which will adjust the values to add up to 1. Got it? But this is how you train it. This is called one-hot encoding. So what that means is whenever you, so let's talk a little bit about that one. So one-hot encoding just means how you give data. So if it's a cat, so let's say you have cat, dog, bird, right? We have a 3-class problem. So when we encode, if it's a cat, then 1 0 0. If it's a dog, 0 1 0, right? Do you see that? And if it's a bird, is what? 0 0 1. Perfect. That's called one-hot encoding, and it's the way that we feed the data. One-hot encoding. Because the mechanism works like this. It predicts these values, so then we have certainty of what we're looking at. Questions about that? Nope. All right, so this was the remember, this is architecture. When you're building your neural nets. Now, the multi-layer perceptron is basically going to be ... Let's stay with the 2 values, 2 neurons, 2 classes. It's gonna but in between, we have 1 more now, you see, and that corresponds to this, additional, this one here, that additional layer. And so you can define however many neurons you want in there, but usually you follow this funnel shape. What that means is force the algorithm to learn with less. You see that? If you give it too many resources, it'll just like, it can literally start copying things and, you know, and not really, you know, so you'll end up with this exact same thing over here. Think about it. If you had 1 million of these, sometimes it would try to just copy them and see what happens. It might go with that. All right. So that's why funneling the data is good, because it forces it to you know, it at the end of the day, its objective is to minimize error, right? To get the highest label. So it's trying this and that didn't work. So now I'm going to change the weights up or down. Try this, didn't work. Okay, now, you know, let's go down. Oh, that worked. So, you know, and it starts going in a direction. Okay, remember, it's an algorithm. So it's not like it, we'll talk today, we'll talk about that analogy of the mountain range, the giant. It may not find the best solution. It finds an optimal solution. That's why it's called optimization, not bestization, right? So there's no such thing as bestization, but there is optimization. Okay, so in optimization, you try your best, right, with the algorithm, and hopefully you get to the correct answer. But it, you know, as these get more complex, it may turn out that they don't, the term is converge. So the terminology that you would say is it didn't converge to the optimal. And what that means is it wasn't able to find it. Okay, just because it went in this direction instead of going in that direction, you see? And so that happens. This is why you repeat. That's that whole thing with the epochs where you're constantly repeating and randomizing things. It's almost like all of you are going to go search for a treasure. David, you go that way. Lenny, Jake, you know, and see who finds it. And then you're going to share the winnings or kill each other, whichever one. You say that now. But you get the point, right? So you get the idea. So that's the sense of it, right? So we'll get to that when we talk about the optimization part. So now this is the architecture that you want to follow. And if you look, you have this, right? And so now this is basically, oh, and then this one is connected, of course, as well. You see that? So what's different is there's this hidden layer. Now, there is the activation function, of course. You need what? Which one do you need here? Now you know, so which one? Which activation do you put here? Of all of these, which activation? This is the input. This is the output. This is one hidden layer. The output is going to give you this, right? Cat and dog. The probabilities, if you want to think of it that way, that it is one neuron or the other. So which activation function should you use here? Take a guess. Nope.
I don't remember the name.
You sure about that? Look at these activations. Which one do you use for that last layer where you're predicting the classes?
Sigmoid?
If I use sigmoid, it's going to give me 0.8 and 0.4. What happens if I use softmax? They're going to add up to 1. Intuitively, which one would you say is better? Softmax, right? Because they add up to 1. So that's where I was going with this. Yes, you could use sigmoid. It might work well. Remember what I said. Softmax, though, yeah, exactly. It ensures that they add up to 1. It's going to be slightly even better differences. You see that? And so what we might want to use here is softmax. How about here? this also has activation functions, as you will see later. What would we use here? Is not softmax again, no. So we go to the activation functions. Not sigmoid. I mean, you don't know, so you have no basis to guess, but this is actually the realm of ReLU, where experiment and don't, you know, I don't even think it was like theoretically somebody said, oh, it's this one because of this. They tried all of them. And at the end of the day, ReLU, the rectified linear unit, turned out to provide the best results. The values are positive, they're linear in a sense. So, do you guys see that? And so this is the idea. Question? You don't see what? No, I don't. No, I can't tell you one. That's my whole point. Well, it's not that you should go with it. This is a lot of this is experimental. A lot of the time, what they do is, okay, we're just going to change all the parameters and see which one is best. And there's certainly tons of experiments. So this is like years of trying these out. Then somebody, I guarantee you, there's somebody that can tell you why. I don't know.
So don't go with it, but based on everybody's previous
Experiments, yeah. Everybody tries all these models, and ReLU, as I said, you know, a lot of people tried ReLU and they said intuitively it's the best, right? And then I read a paper yesterday, and now they're using the Gaussian linear units. You see what I'm talking about? So ReLU might have, somebody might say, oh yeah, because of this, and then somebody comes up with a new one that's even a little bit better. What I can tell you is that the values here, instead of being from 0 to 1, are from 0 to whatever infinity. Actually, this is actually, I did this wrong. I know now how I should have written this. Right? Because if the value is positive, it's just linearly that value. But if it's negative, it clips it at 0. There's some intuition somewhere as to why that works. For that particular stage of the neural net, remember, it's applied here. Here, though, we want the softmax because we want the values as we have been describing them. For them to look like probabilities, but for them to add up to 1. Now, notice there's another, makes sense also. These, the one hot encoded vectors, what do they add up to? 1. If you look over here, look at all of these. 1, 1, 1. They all add up to 1 as well. There's that, right? But yeah, so these are the main ideas of it. All right, so this is the diagram of it. The probabilities with softmax just come out to be, again, 0.7, 0.3. They do add up to 1. And then the last one in architecture for the deep learning algorithm. So hopefully I'll have enough room here. I'll make this small. ... And then here we have our outputs. And I'm just going to use 2, but you know, it could be more. MNIST has 10 of these, right? MNIST has 10. So actually, just for variation here, I'm going to do 3. Okay, and then now in between, in the deep learning algorithms, we have many. ... Now, is it guaranteed that the more layers you throw at a problem, that the better it'll do? What do you guys think? Not necessarily, right? Right, so the performance usually goes like that, and then eventually starts to like do this, right? Drops. However, there's a little piece to that is currently also under like research, right? So it's not very clear there. This assumes that the data stays the same. Do you know what I'm saying? Like if the data, you have like 160 gigabytes of data, right? Let's say that's your data. And that never changes, right? That never changes in your training. So eventually, as you add layers of architecture, it goes up, up, up. Eventually, you might see this. However, there's a theory that as data grows, so performance will continue to grow, let's say, as long, oh, that's a good way of saying it. Performance will continue to grow as long as both the data and the architecture grow. And probably the intuition with that is like you have your brain, right? And you can process all the stuff about physics. But now you have to learn chemistry, math, biology. But if we throw another brain in there, you see what I'm saying?
Yeah.
So if I throw 4 brains, one for each one of those, in the aggregate, and they're somehow connected, they can do it. Or even as a group. Do you see my point? Yes. It's not possible, right? It's not possible. Today, except actually that's a good point, right? Today we have 2.5 terabytes. We couldn't learn anything with the perceptron, but we throw a much more complex architecture, it learns. So by that analogy, in 50 years from now, it won't be, I don't even know, it'll be like, what's the next one after terabyte? Petabytes? And then after that, who knows, right? But something, you know, even larger like that, right? You know, and those are probably things like in the realm of like particles, right? That require a lot of information, you know, those kinds of models, DNA or something. And the architectures will have to be even larger to support all those parameters. But yeah, that's a good analogy. So apparently this might be true, right? Seems intuitive that this is performance, right? And these just, they're basically growth in data and architecture. So as long as this maintains, performance should go up. Or no, there's been some examples where this seems to happen, for sure. Okay, so that has been shown. That really what matters is more architecture, but more data. You know, one and the other. However, if you only have a fixed data set, then yes, if the data set is not growing, then eventually the architecture, more architecture will just make it drop. Okay, drop performance. So that has been shown for sure. I mean, you guys will see it actually in your project. I encourage you to run that exact same experiment. You can, right? You'll have some data set like Lenny is doing the Titanic, I think. He's got like 30,000 samples or something. And so based on that Titanic data, you know, it'll probably be very easy to classify, I would think, but try, you know, a multi-layer perceptron, that's 1 layer, then 2 layers, 3 layers, 4 layers, 5 layers. You can measure performance with all of those. Eventually, you'll see that more layers does not mean better results. Got it? Yeah. Right, and that's, you should all do that. Okay, but in this algorithm here, we've got more neurons basically, and so that's what multi-layer is, and then they're all connected. So there's more. Again, here, there's activations, of course. That doesn't change. You guys already know this. And these are also activations. There's no activations on the input, though. Notice that there's no activations there usually. And these would be ReLUs, generally. But this one is a Softmax. Got it? All right, so that should be, and then the result is still the same. 0.4, 0.6, add up to 1. It's, oh, this is actually 3, so let me be consistent here. So it would be 0.2, 0.1, 0.7. See that? So it gives you, and then you just pick the ID of the maximum value. So usually you use a function called argmax. The argmax just returns the index of the highest value. So in this case, it would return 2 for 0.7. And then you know it's class 2, and then you just look up what that class means. So it could be bird in this case. Is this clear as far as architecture? So this is the way that we look at this architecture. This ties into how we looked at the functions over here, okay? And so we've got that. And then we've talked about activation functions. And then we've also talked about Hut encoding. We kind of talked about this. The last thing we need to talk about is the blue part, right? Which is the optimization. Right, which are usually referred to as the loss function. So what happens is if we go back to that example, the initial one, we've got the inference function. So every algorithm has an inference function, but then they have basically a function that governs the update. Okay, a function that governs the update, which is the behavior that we're trying to follow, right? And so we said that this is MSE, and for the rest of them is cross-entropy. So we're predicting these probabilities basically for that something is that class versus another class. So let's take a look. So there's really, even though we have 5 things here, now we just have 2 loss functions, okay? So we have basically 2 camps. We have for linear regression, usually these are just referred to as regression problems. And then we have for the classification, which would be logistic regression, multi-layer perceptron, deep learning. So they all basically just use the same loss function. So here we use MSE, mean squared error, least squares error. And then here we use a function called cross-entropy. Okay. And what that means is, you know, it's really these, although we can graph these and look at their behavior, really what this means is, what is the function that governs how we're going to do the update? Do you see that? That's basically what it is. So in linear regression, if you remember, our goal, you know, we have points, right? We have all these points. And our goal is to fit a line, right? So we could fit that line, well, let me exaggerate it a little bit. That line, we could fit that line. I mean, any of an infinite number of lines. How do we measure things? At point X here, X whatever, Xi, we see the real Xi is right there, yeah? But the predicted is there, right? The function would say that for Xi, this is the point, the real one was here. You guys see that? So then we take the difference. See that? That difference is the difference between the real and the predicted for Xi. So that delta, I'm going to erase this part here. that delta is what we want to predict, right? And then over here, if I have another one, xj is like that, xj, so that would be, let's say, this point over here, but the real one is here, so that we take the difference, right? So then this is going to be the sum of all of these, right? So it's going to be delta, let's say, xj plus delta xi dot, dot, dot. So for all the points, we see where they are, and we calculate in this. Remember, this has to be a straight line. It's not like this, right? It's not the distance like that. It's the distance in a straight line. So because we say for this x, right, the j falls here, the real one, but then the predicted falls there. So then, you know, that's the difference. We take the sum of all of these, and then that's one set. Let's call it A, but then we have this one, B, right? For this one, xj falls here, but the predicted would fall there in the function. Now, this is obviously highly exaggerated, but look, that's a much bigger delta or difference. Do you guys see the difference? So which one do you do this multiple times, but you pick A because A minimizes the sum of the errors. We usually say the sum of the squared errors because we want to take, what about values on the other side, right? So if this is the value and then this is the predicted, right, we would have something like that. And then some of them would be plus, some of them would be minus, right? And that would make everything zero, basically. So, but if we square them, we get rid of the symbol. We just get the distance. Does this make sense? This is what you do for linear regression. And then this gives us the function y minus y hat squared divided by n, right? So the mean squared errors of all of them. So, you know, you write it as the sum of the errors. So the sum from I equal 1 to n, right? And then this is going to be I and I. Do you see that, guys? This is the loss function for linear regression. So now we can go over here, and where we have y, w, x plus b for linear regression. Actually, let me do it like this. For linear regression, we can now, we know that there's two functions. So this is the inference function. So this is the inference. And then this is the loss, which determines how you learn. So the inference is just y equal wx plus b, which, as you guys know, is just a line, right? Graphically. You know, this is in 2 dimensions, obviously. Now, for the loss function, we just said, well, it follows this behavior over here. So then it's going to be 1 to n, the difference between yi and y hat I. But really, you can also write it, so y hat I like that, squared, right? But this can also be written as, you'll see it sometimes like this. Imagine that y hat is the real one, so then this is the predicted. So then now we would say, instead of yi, we would just say w x plus b minus y hat I square, because we're just plugging in this in there. Got it? And so you'll see that as well. That's the loss function. Now this, importantly, can also be represented as a function. So there's a second graph that's associated with, so in the algorithms, you have two functions, the inference and the loss, but you also have two graphs, okay? The graph for the inference, which is this one, and the graph for the loss, which is this one. What does this one look like? Because of the square here, it makes it quadratic. Quadratic function, you guys probably remember that, right? You used those before. Quadratic functions have a really neat property. The neat property about quadratic functions is, let me do this a little bit better. It's that bowl shape, but there's a bottom. There's always a bottom. Since you are going, so if you think about it, you are trying to minimize this, right? And this is represented by this function. Do you guys understand this? So if the search that you're doing for the optimal set of parameters is happening but governed by this function, that's equivalent to thinking that the search is happening in this function itself. You see that? So you're looking for the parameters. So this means cost, and this is just literally that parameter that you're looking for. So if I have this W here, W1, it maps there. Do you see that? Why? Because this is the function, but notice that the parameter that I put in there now depends on W. So whereas before we had yi and yi minus y hat I, right? Now I have this, but I changed that y with W. And disregard bias, but it's kind of the same. So what does that mean? It means that if you change W, this changes, right? So so the result of this is usually denoted by a J, is that this J, the cost, is gonna be that for this W. But that W represents that this line looks like that, because it's the slope, right, of the line. And so if I pick W2, what happened to the cost? It went up. You're trying to minimize that. So what is the optimal point there? Where would it be? The bottom, right? So W3, let's say, goes there, the cost is minimized. So that would give you this line, which is the one that fits the data most optimally. Do you see that, guys? And that's why, you know, I was giving you that idea that this is the procedure, but it's governed by a function. All functions can be plotted, right? And so have a shape. When you see a little square parameter, they're quadratic. And so they look like that. That's why linear regression is so popular, because it has an optimal solution. Neural networks don't have that. So now, but if you guys understand, did you guys understand this? Did this make sense? So if you understand this, then it's good, because now we can extend the analogy to classification, right? So if you remember, only linear regression would use that notation, or that cost function. So we're done with that one. Now if we just cover cross-entropy once, we cover it for all. That's the beauty of it. So cross-entropy then, but cross-entropy has a different objective, because now remember the values are this, so they're encoded like that, right? And so now we have to think, okay, what do we need to do? We need to think of cross-entropy here as what, you know, the problem that we're trying to do is we're trying to fit so now we're trying to find still a line, but with a different objective, right? Instead of it being a line that fits this data, it's a line that best separates. So there are now two sets of data, or it could be a three-class problem or something. Do you guys understand? So this is slightly different intuition, but again, logistic regression has two things. It has an inference and it has a loss function. So we can now take a look at this for logistic regression. But really, I will just generalize it to cross-entropy, because this applies for all of them, right? You know, deep learning and so on, all neural nets. So then we still have the inference and the loss, just like we did before. Okay, the inference and the loss. The inference is still y equals wx plus b, but remember, it runs through a function. And this can actually be neural networks as well, so there can be more layers in between. Now, the objective is now to predict a value between 0 to 1, right, for multiple parameters. So here for that, we have a new cost function, which we're gonna wrap up with that today. So I have here. There it is. The cost function for cross-entropy, and this is only for binary. There's also for multi-class, it's a little different. But for binary, the cost function will be minus log of g wx plus b if the label is equal to 1. This is the real class. Or it'll be minus log 1 minus g wx plus b if y equals 0. So it might sound pretty complex, actually, but it's intuitive. So this, just like the other one, right, has a graph. And now let's take a look at that graph. And as it turns out, there's actually two of them. So we have two graphs here. This is still the cost, right? And this is the value that we're going to calculate here. So this is this parameter, and this is for this parameter. So if it's 1, if y is 1, if it's this scenario, right, then we use this function. You don't have to worry so much about this function. Just know that it follows this graph here. This graph here looks like that. That's basically what this means. It's a curve that looks like this. So what is your objective when you're doing the optimization? If the class is 1, right? If this class is 1, what do you want? You use this function because this function allows you to optimize. This goes from 0 to 1, right? Allows you to optimize the value. So the cost will be lowest when it's 1. You see that? And highest when it's 0. So that's the behavior of it. And then when you do the other one, let's say that y is equal to 0. Okay, that means that you want that value to be towards 0. So you do something like this. And so now this is 0 and 1. So the cost will be lowest when it's closer to 0. If it's like here, the value is getting high to 1, the cost goes up. And this is how basically you force the algorithm to learn that. So it's like saying, I'm going to force you. If the label is 1, I want you to change the weights to predict 1. You see that? That's it. That's all you have to understand. If the label is 0, like the real label that you got there is 0, what do I want? I want you to change the weights in the inference function, right? So that what? So if it's 1, you should learn to predict 1s, right? And so you're always, so if this is the label 1, you use this function to train the model. If the real label is 0, you use this function. Basically, what that's going to do is it's going to force the weights towards 0. Okay, and this one will force the weights towards 1 because this function looks like this. It starts to go down as the value increases, and this one starts to go up. Does that make sense? Yeah. All right. That's it. So hopefully that makes sense. The idea is, so it's almost like this. I have a model. I want you to learn, and you're like, okay, how do I learn? I don't know how to learn. Look at that graph, right? You're 1 right now, and I want you to learn to predict 1s. So then you use that equation always, right? That little tweak. So that's why you're plugging in these logs here, that they represent that value. Okay. Now to generalize this to deep learning and to kind of conclude, in deep learning, you have the J or the cost function. And because they're so complex, right? So there's so many layers, the actual function may look like this, which is a way of saying it looks like a whole bunch of these things together. You see that? You're almost like with this building, that was logistic regression, right? Where is it? In logistic regression, we just have something very simple as an architecture. So it really just ends up looking like a very simple, like this. But in a deep neural net where we have tons of layers, our cost function no longer looks so neatly like that. It looks more like this. You see that? But it's still, this is the cost, and this is still in terms of the weights. How do you know where to start? That's why we start random and we repeat it multiple times. The goal is sometimes the algorithm begins here, right? And then the algorithm has to decide if it's going to go up or down to find the weight that minimizes the cost. So what would be the weight here? So if this is 1, 2, 3, 4, 5. I'm using those as index positions, not as actual IDs. What would be the position in the function that would minimize cost and therefore tell you that you found the optimal weight? W3 would be like there, right? W2 would be there. Is there a better one in the function? That a point in the function that minimizes cost? Now, which one would it be? Okay, like here, right? That's this point, although it's not that big of a difference from W2, right? But let's call this one, as you said, 2.75. That point is, in theory, the one that minimizes the function. In deep learning, you don't know this. You don't know. There's no way to arrive at it. You see what I'm saying? Theoretically, you're like, oh, I'm there. It's a search in the function. That's what I was trying to say. So obviously, if you have a quadratic function, like we do in linear regression, it's really neat because you're going to find it if you find the path going down. And then you have logistic regression, which is simpler. Neural nets look like this. So that's why sometimes you want to start here. Other times you might want to start here. Other times you want to start here. If you had started here, unfortunately, what's going to happen is you're going to probably end up there. The algorithm will end up there, and it may never find that there was this solution that was a little bit better. So this is called the local minima and the global minima. The objective of the algorithm is to, in an optimization problem, is to find the global minimum, but you're not guaranteed to find it. And so a lot of people spend a lot of time researching this, and they haven't cracked it. Stochastic gradient descent, the algorithm we currently use for all of deep learning, does it this way. Jeffrey Hinton keeps saying, you know, somebody's going to solve that, and then everything we do is just going to go out the door. But until they do that, this is the workhorse that does it. You find this function, the optimization function given the neural net, and you just start searching. And so that's why you always want to, your weights are always randomized, and you repeat it multiple times, and every time it's a different randomization, and you feed the data shuffled around, because eventually you hope, but by doing that, you will fall here, and then boom, you got it. Think of the stock market, right? So this might be pretty good at predicting something in the stock market, but this means you made $1 million last year. This one means you made 10 million. You see the difference? So you might be happy with $1 million a year, but you'd be a lot happier with 10 million, but your algorithm just didn't find that optimal. So that's a good example of that. It's a trade-off. And currently there's no solution to that. Got it? Questions about this? That's why I said, now, where does the giant fall into this? The learning rate versus You see the difference now? That's the learning rate. Do you understand? Huh? Yeah. So small learning rate, it's not a giant, but a very tiny person. Takes that person a very, very, very long time, and they may never get to the end if it's too tiny. The giant, what happens to the giant? Giant steps here, and it never steps down here because it just doesn't. It jumps from here to here to here, here, never reaching the bottom. So that's why this might be 0.01, the good learning rate that will allow you to and eventually get to the bottom. Do you guys see that? So that's the learning rate and how it fits into the whole idea. All right, so I think that's great. The last thing I could mention possibly is your question might be, how do you decide if you go in that direction or that direction? That's calculus. In calculus, on a function, you can calculate when you take the derivative of a function in terms of a specific point. So for instance, for this point, I have this function, I take the derivative of it, I'm gonna get a tangent of it. And this tangent looks like that, whereas a tangent here looks like that. So there's slope basically. You guys see that? And based on that slope, I know if it's negative or positive, and that's how I know if I should go up or down. Like if I'm going up or, or I should be going down. But that, that's beyond. I said it only so that you know where calculus fits into this. You don't actually, we don't actually have to worry about it. All right, but that concludes. Yeah, that's it. So what we're gonna do on Wednesday? Yeah, Wednesday is we're going to just go over code, logistic regression code, which is just last week's code, but a little bit more. And then the multi-layer perceptron code. We'll wrap that up. Maybe we'll start the deep learning one, but otherwise we have plenty of time. Deep learning is the last topic, and we have still 2 lectures for it. That's it. But as far as theory, this was technically like the last theoretical lecture. And then now just finish up with the code, the algorithms. All right, so we'll stop here for today. And I'll stop the